Hello everybody, my name is Helen Maynard-Casely. I work for the Australian Nuclear Science and Technology Organisation. Just before I get started, I would like to acknowledge the Dawag people, the traditional owners of the land of which I am speaking to you from today. I'm very thankful for the opportunity to tell you a bit about our research in this session. I do realise that probably I'm coming at things a little bit left field from many of the other speakers in this session. And I want to talk about organic mineralogy in a very specific context, and that is on the surface of the largest moon of Saturn, and that is Titan. So Titan is one of a number of ocean worlds within our solar system, and we call them ocean worlds because many of them we believe and have observations to support have large oceans underneath the surfaces of them. But they do also have quite a big variation in their landscapes. And these landscapes that we see, that we observe from spacecrafts and from telescopes on Earth, are down to the variety of the materials that make up these surfaces, from the bright spots of Ceres all the way through to the flowing glaciers on Pluto. And I believe that this is a really great and an interesting frontier for us to study, especially as crystallographers. So what are those materials? Well, there's a bit of a chemical change as we move through the solar system. There's a number of reasons for this. But when we're talking about the asteroid belt, so Ceres and Vesta, the larger objects there, we're talking the surface materials are things like carbonates, sulfate hydrates, and some organic molecules. The Galilean moons, so these are the large moons of Jupiter. We're talking about ice, traditional hexagonal ice, and a few other phases, chloride hydrates and sulfate hydrates. When it comes to Titan, and we'll talk a bit more detail about Titan, we've narrowed Titan down to 3 types of materials, so I'll talk about that a bit more. And if we get further out to the edge of our solar system, with Pluto and the Kuiper belt objects, the KBOs, things like nitrogen, methane, and carbon monoxide become the dominant surface materials. And all this information has been garnered from spectroscopic investigations, and they've given us a great wealth about the chemistry there. But we don't necessarily always know about the material properties. So we know the chemicals there, but we don't know the surfaces, the materials, the actual crystal structures that are forming all the time. And that's exactly what we're trying to tackle. So we've called this topic cryomineralogy, just to distinguish it from earth mineralogy. And cryominerals are materials that are naturally forming on other planets, and these are usually species that are liquid and gaseous at standard temperature and pressure. And unsurprisingly, we're approaching the study of these with scattering experiments, with Raman scattering, X-ray diffraction, neutron diffraction, and some inelastic scattering a little bit more now. And we've got a sort of a process where we go through the crystal structure. A lot of these cryominerals have order-disorder transitions, so we're looking at that. We then try and vary the conditions and probe the physical properties. Some of these cryominerals have some really interesting things that they can do, from polymerization to pyroelectricity. And we can also start to think about how we probe the mechanical properties as well. A lot of these small species have plastic phases, which has never really been thought about how the plastic phases work in a geological context, but that's going to be very important for planets like Pluto. So why the focus on Saturn's moon Titan? Well, it's a really fascinating world. It's nearly the largest moon in the solar system. In fact, the reason it got called Titan is because we thought it was the largest. Unfortunately, it got picked to the post by Ganymede, which is a huge 50 kilometers actually bigger. And part of that was because actually Titan has a really thick atmosphere, and originally people had mistaken the atmosphere for the diameter of the planet. Of the dwarf planet. It's actually bigger than the planet Mercury, and it's a great place for extending our understanding of planetary processes and astrobiology. It's if there is any astrobiological activity going on there, it's going to be very different basis to that on Earth, and that becomes very exciting for us to probe and to think about. So everything, or most of what we know about Titan, has come from the Cassini spacecraft. It applied sort of spectral, some gravity, some radar data, and revealed a surprisingly Earth-like world, some very Earth-like processes going on. And one of the most significant discoveries in the context of this work was the prevalence of small organic molecules on the surface. So where are all those big sort of inventory of molecules coming from? Well, it's coming from that atmosphere that we just mentioned. So the atmosphere of Titan is made out of nitrogen and methane, and interactions from the solar wind and radiation from Saturn causes those to radicalize and to form other species. And there are a number of people who've put through astrochemical models. I've forgive a lot of text here, but I'm just want to show you that some of the number of astrochemical models that have been applied to this problem, and the big inventory of species that they believe have fallen out. So as these species fall out, they're then going to rain down onto the surface of Titan, and this has been happening for give or take a billion years, and we've built up this large carpet of organic molecules, and it's in that carpet of these species where all of that interesting geology that we see is actually happening. Now, with that, a few years ago, we thought about some of the implications of this and the prospects for minerals on Titan, and we've divided them up into three different categories. So the molecular solids, these are the pure materials that have just sort of crystallized on the surface. The co-crystals, so these are when they combine to form new species, and I'll talk a lot more about that in a bit. And then we talk about the hydrates as well. And the hydrates where the organic molecules have interacted with the ice layers below as well. So that's I'm actually going to talk backwards, and we're going to go from the hydrates, which we believe when we talked through this paper that they were going to be the strongest materials, the sort of the harder rock on Titan. And then we believe that the co-crystals would be a bit softer, and then the molecular solids, mainly governed by van der Waals interactions, the softer again. So already we're beginning within this sort of mineralogy suite to think about their physical properties and how these processes would occur on Titan. I'm just going to apologize if you can hear there's a helicopter going across around at the moment. So hopefully that's not too distracting from me from going on. So hydrates are very important on Titan. So gas hydrates, so these are water cages where gas hydrocarbon molecules live inside. They're often non-stoichiometric species. One of the reasons they are very important in the Titan context is they were believed to have been one of the reasons that we still have methane in the atmosphere of Titan. When it was first observed that in the atmosphere of Titan by Gerald Kuiper back in the 1950s, it was quite a surprise because it was believed that all the primordial methane within the atmosphere should have left by now. So it straight away suggested that there was some replenishing going on to the atmosphere, and so there's that replenishing geological activity. And so that was one of the reasons that Titan got picked for study very early on. And the hydrates there's a number of models that show that they can form in the interior, and then they can sort of release their methane and their ethane going onwards. But one of the sort of puzzles has been that Titan is the standard surface temperatures of Titan is around 92 Kelvin, and it's around 1.5 bar of atmospheric pressure. This isn't traditionally enough in the traditional understanding of gas hydrates to form them. And so there was quite a bit of a question of whether hydrates could actually form on the surface of Titan as part of this replenishing and potential geological activity. And here we're interested in sort of, we've got these large ethane lakes on Titan, and if they're interacting with the bedrock, the ice bedrock below, can that actually form hydrates sort of in that surface context? And we've done a number of experiments. These are done with Raman scattering at the Jet Propulsion Laboratory, and they found that when you actually put liquid ethane across onto a bed of ice or grains of ice, you can actually start to form ethane clathrate. And we measured the activation energy of this and got the kinetics, and then pulled it down to 90 Kelvin. And what we found that is that yes, you can form these gas hydrates, ethane hydrate, in a reasonable timescale. So it would take about a year rather than 150 Kelvin. It takes about 60 minutes to reach 60% completion. But in a Titan context, 1 year, 1 Earth year is actually quite rapid. And so straight away is a really nice answer to that question, that yes, we can form hydrates on the surface of Titan. So, and that's a little bit about the work we've done on hydrates, but what about those co-crystals forms? So the hydrates will only form sort of, we've got that bedrock of ice with the organic layer over top, but what about all those geological processes going on in that organic layer? And a nice example is sort of like evaporite lakes. So if you flew across Titan, as Cassini did here, it's not that dissimilar from flying across Australia, where you've got all these evaporite lake beds. But of course, these are evaporites with water, and it's a little bit too cold for that. What's an evaporite when your solvent is ethane or methane? And a number of years ago, the group at JPL who sort of started this whole field had a look at this and saw that, you know, when you interact benzene with ethane, you get quite a big change. They studied this with Raman scattering, and we were able to then pick up and do some diffraction with that, and it revealed quite a wonderful framework structure. So this is our benzene ethane 3-to-1 co-crystal, where the benzene forms a framework and the ethanes live down the channels in that. So this is what we thought was potentially the first Titan evaporite. One of the really lovely things to have happened in the last 20 years is another group have started looking at this, and now we're all working together, which is even better. And they found that this structure is also occurs with benzene and acetonitrile system, and it's pretty much, you can see, a very same idea. You've got the benzene framework and the acetonitrile living down the channels there. And in their paper, they even actually tried to look at some interactions with methane and saw something, ethane, and they saw something else strange happen. So there's some really interesting potential processes and dynamics going on in these materials. So straight away, we've got a couple of really interesting Titan minerals. But if you recall back, not a few too many slides ago, there's a big list of molecules, benzene and ethane and acetonitrile being only 3 of them. What about all those others? So we've been screening and trying to find other co-crystals, and as you can see, it's a big list. And here's some nice micrographs that show some of these co-crystals as they formed. We have a number of them we've got structures for. So these are the benzene ethane and the benzene acetylene again, but then these are some of the layer structures. So a lot with acetylene and ammonia, acetylene and benzene here. And we've recently actually just written a really nice review paper about this work and where we think it's all going. So I really urge you to go and look up that in the accounts of chemical research as well. And one of the things it's revealed is actually that despite the fact these are all quite simple molecules and these are all quite, you know, you'd have thought that all their intermolecular bonding, though weak, would be quite similar, already shows quite a variety of physical behavior, and no more show with just good old thermal expansion, where you can see the acetylene ammonia, one of those layered materials, has a massive thermal expansion when compared to the other materials. And actually, one thing that's quite surprising is how big it is compared to acetonitrile acetylene, which is reasonably similar layered material in some ways. So a lot more to do. And as I said, a lot more to do. Here is the sort of, paired up diagram, and in each of the sections I've coloured in where we've got the material and the structure, and also where we the number is actually its density in kilograms per cubic meter for the material at 100 Kelvin. So I'm trying to standardize it all and try and understand, at least from a beginning perspective, the sort of relative density of these materials. That's like the first basic, that, if they all pile on top of each other, which one's going to sink down to the bottom and which one's going to bob up to the top in terms of buoyancy over a sort of processing time scale. You can see there's a lot of blanks there. There's a lot more materials that we've yet to see if they can pair up, they can make co-crystals. So, and we do urge anyone who's interested to try some of these, please do get involved, and we'd love to grow the subject a lot more. But hang on a moment. You'll notice that on the where I've looked down at just the pure material, there are a number of numbers missing. And this is where the next level goes, because of course, with when you're thinking about co-crystals, you're like, all right, well, if you know the structures of the co-formers, can't you just sort of like calculate if they're going to make co-crystals? Well, that's really hard when you don't know the crystal structure of the co-former of the pure material. And in a number of cases, that's exactly the problem. In fact, butadiene, butene, diacetylene, hydrogen cyanide, propadiene, and propyne have no published crystal structures. And if you don't believe me, you can go check, because I absolutely have. And in some cases, this makes sense. That hydrogen cyanide is one of those materials that the astrochemists have observed, but we don't necessarily have, you can't ring up and get it from Sigma. It's quite an unstable material. And then the other thought is that even ones with known and published crystal structures, not all of these have been determined all the way down to 90 Kelvin. And so we don't necessarily know if that's the right crystal structure for a Titan context. And one in particular for that is acrylonitrile, and it got a lot of attention recently because a group, Stevenson and al, suggested that because it's a polar molecule, that it could actually form a membrane. And then the idea was that, if this can form a membrane, maybe that's the start of a potential astrobiological system. But if the interesting thing is that the structure they're basing this off was determined at 170 Kelvin. And so I'll talk a little bit about some work that we've done along there, along the way. So we've been going back to absolute basics and trying to work out some of the crystal structures of these molecular solids. So both we've recently had some advances in both butadiene and propyne. We are mainly solving these from X-ray, lab X-ray data in the case of butadiene, and synchrotron in terms of the propyne. The butadiene is quite interesting. Clues back in 1940, working at the Royal Institution, actually it has an indexing of it. It's a really lovely paper in terms of how you would index something when you don't have all of the tools that we have today. He actually indexed quite a large orthorhombic cell, but what we've determined now is we believe that the structure is actually the primitive monoclinic cell within that. Propyne is a little bit complicated. I should say one of my ways of approaching the structure solutions of these is to go find another, or where it's a co-crystal somewhere else, and then I use that as the basis for my rigid body, and then I add that and do simulated annealing in order to solve the structure. With propyne, there are no structures that I can find with propyne within it. So actually constructing the rigid body was sort of like a lesson to begin with. It was sort of like, arrange it a little bit and look at the bonding. Okay, that seems to make sense. And then feed that into the simulated annealing. It actually has a number of phase transitions. And actually, as I speak, we are collecting data through the APS mail-in program to see if we can characterize the other phase transitions. So this is very much a watch this space. Hopefully we'll get the publications on these materials out pretty soon. But even when we know the structures, some surprising things can happen. And I thought the story here starts with acetonitrile. So acetonitrile, pretty well studied. It's a solvent used in many people's labs. We know it has two phases, an alpha form and a low temperature beta form. We did some neutron diffraction. We just wanted to see the thermal expansion. As you can see, we obviously, this just shows how awesome Wombat, the instrument that I run, is, where we can take data within 1 to 2 minutes, even from hydrogenous materials. And so we've got a really nice thermal expansion there. So that was really nice example. But when the honours student who's working on this came to do this in the lab with X-ray diffraction, James, he found that something really strange kept on happening. And as he cooled, he would actually still get the alpha form, the high temperature form, at low temperature. And it depended. He took some initiative and changed his rate of cooling. And I actually feel terrible now. I've forgotten to put the reference here. So the reference is Choi et al. And it's in the ACS Earth and Space Chemistry. It was published last year. And it found that this was depended on the size of the capillary and the rate of cooling. And what we believe that James has discovered is the very first phase trapping of a Titan mineral. So this is analogous to what happens in silica and cristobalite, where the high temperature cristobalite, if it sort of comes through a volcanic process and cools quick enough, you can actually trap that higher temperature form at lower temperatures, and it can exist. So that was quite the discovery, and something that you don't necessarily think is going to happen with such a simple material. And we believe that this is related to strain within the crystal structure, and so is potentially a probe of the mechanical properties as well. So straight away, there's something else that we can measure. And I said I would talk a little bit about acrylonitrile because it's sort of the hot topic in at least molecular solids for Titan. It's that material that, you know, if you pick up bowling balls, is polyacrylonitrile, so it's the starting material of that. And there is a known crystal structure, but it is quite highly disordered. It's sat there on a mirror plane and so flipping across all the time. There's been some phase transitions implied by spectroscopy, but none characterized by diffraction. So we've done a neutron diffraction on the hydrogenous sample here again. And what we've discovered is we do see phase transitions, we see a new form, and we're having some trouble solving it. But the clue that we got from the acetonitrile has really helped here, because now what we think is happening in interpreting the acrylonitrile data is we think that alpha form, that disordered form, so we're now calling them alpha and beta, that high temperature form is actually being trapped at lower temperatures. But one of the interesting thing is the mechanism behind this is going to be very different. So this is actually something we're seeing in the neutron diffraction. So those larger volumes, that 6 millimeter can that we've got of this stuff is showing this. And also, as opposed to acetonitrile, where the high temperature form isn't actually that disordered, the acrylonitrile high temperature form is disordered. So it's something very different that we're seeing. And hopefully now we've sort of cracked this and we've realized that this is what's going on, we can solve the novel beta form, which we believe is probably the more stable low temperature form. Although, and of course, until we've got the crystal structure, we can't perform the optimization calculations to find out for sure. And we're hoping that once we've done this and we can look at the intermolecular interactions, we can really add something solid to this debate about the atzosome, which is that membrane that people have predicted in acrylonitrile. So that's another sort of watch this space going on. So looking forward with the Titan Minerals project, we've got quite an important deadline coming up in 2035. I believe the Dragonfly mission should arrive at Titan, and we're basically rushing to characterize as many minerals as we can before we get there. But we really want to think out what happens if they get in a geological context, what happens when they get buried and things. And of course, many of you might know I have a background in high pressure. So I'm very interested to know what happens to these intermolecular interactions under slight pressures. These are very weak interactions. So slight pressure is going to cause all sorts of interesting things to go on. And what happens with processing? What's the potential for substitution in these minerals? Are we going to get more complex? We've already seen hints of a ternary species, a ternary co-crystal. So there's a lot more complications to have. Again, if you just think about the context of Earth mineralogy that has been studied for thousands of years, we've only really begun to scratch the surface of Titan's organic mineralogy. So just to summarize what I've been talking about, as I said, Titan's organic minerals are simple chemicals, but they're not well understood as solids. Hydrates with ethane can form under Titan conditions, very exciting result, but it's a liquid ice interaction. We've already identified a number of co-crystals between these small organic molecules and found that they're all stable under Titan conditions. But also work has exposed that even some molecular solids are uncharacterized, and showing some really surprising physical properties. So I'd like to acknowledge the University of Sydney, Jet Propulsion Laboratory, ANSTO and Argonne National Laboratories for access to facilities to undertake these experiments. More than welcome to catch up with me on Twitter or via email if you have any questions, but otherwise very happy to open this up for debate. Thank you very much for listening.